Hello, this is an Algebra 2 class, and we're looking at exponential growth models. We've already looked at the basic formula or the parent function for an exponential function as being y equals b to the x, where b is a positive constant that is not equal to 1. In applications, it's usually written as y equals a times b to the x, where a represents the initial value and b represents the growth factor. In this case, since it's growth, our b value is not only not equal to 1, but it's actually greater than 1. For decay models, b would be less than 1. In real life, growth is expressed in percents. For example, a 30% growth rate means that 30% of your starting value is added on to what you already have. So you would end up with all that you started, 100%, plus the increase of 30%, which is actually 130% of your starting value. Mathematically, we say that the growth factor b is equal to 1 plus r, where b is the base of the exponential function, and r is the percent of increase expressed as a fraction or as a decimal. So 1 plus r is called the growth factor. Let's do an example. We want to write an exponential growth model for the following example. In 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% per year. Write an exponential growth model giving the number n of incidents after t years since 1996. And then finally, about how many incidents were there in the year 2003. So we're going to start by actually finding the growth factor. The growth factor is b, which is equal to 1 plus r. So in this situation, we have r is our percent increase. So r is 92%, which is the decimal 0.92. So our growth factor, 1 plus r, is 1 plus 0.92, which is equal to 1.92. Now to find the a value in our rule of n equals a times b to the t, we notice that a is going to be the t-intercept. For instance, when you substitute the point 0 in your 1996, which is our year 0, and 2,573, the number of viruses, in for n and t, we're going to find what a is. So let's try that and see how that works. N is 2,573. A is the number that we're solving for. B is our growth factor of 1.92. And t is our year 0, 0 years since 1996. Anything to the 0 power is 1, so we get 2,573 is equal to a times 1, which is a. So the shortest way to do this is when we know the value when t is 0, we know that this is our starting value, or we know that a is equal to 2,573. So our equation that we get then is n is equal to 2,573 times 1.92 to the power of 2. Now, 2003 just happens to be 7 years after the year 1996, so we're going to use 7 for t. So plugging 7 in for t, we get n is equal to 2,573 times 1.92 to the power of t. Working that out, we find out the number of viruses in 2003 is 247,484. Let's look at another example. In the equation y equals 527 times 1.39 to the x, we want to identify the following values. The first thing that we want to identify is the initial value. Well, we've already said that the initial value is our value of a. So in y equals a times b to the x, a is our initial value, so our a is going to be 527. The growth factor is the value of the term b. It's the base of the exponential part of the equation, so our b is equal to 1.39. And then the percent increase. Well, we looked at b as being equal to 1 plus r. So our b here is equal to 1 plus 0.39. So our value for r is 0.39 or 39%. Okay, now we're going to apply an exponential growth model to compound interest. In the compound interest formula, interest is added to an account more often than just at the end of the compounding period or the interest rate period. Every time interest is added to the account, it becomes part of the principal and interest accumulates on it as well. So the more often interest is added to account, the more money that you'll end up with at the end of the growth period. Our formula for compound interest is A equals P times the quantity 1 plus R divided by N raised to the NT power. The A stands for the accumulated amount of money after T years. P is the principal or the amount invested or deposited. R is the yearly interest rate. N is the number of times per year that interest is added on to the principal. If it's done monthly, N would be 12 times a year. And T is our time in years for the growth period. So let's take a look at an example of that. We want to find the amount of money in an account after 5 years. The amount deposited is $500, and the annual interest rate is 2.92%. And in part A, we want to find how much money we have if the interest is compounded quarterly. So let's go through and identify our values for each one of these terms. We start with the amount of money and we want to have it in an account for 5 years. So T is going to be 5. The amount deposited is $500. That's our principal P. So P is $500. The interest rate R is 2.92%. In decimal form, that's a decimal 0.0292. And then finally, the interest is added on quarterly, so N is going to be 4. Plugging those into our equation, we have A is equal to 500 times the quantity 1 plus 0.0292 divided by 4 raised to the power of 4 times 5. As we work that, we're going to work this part all at once. So we have 500 multiplied by 1.15566. We don't want to round that number too soon. We want to be able to take it out as many decimal places as we can. And when we get to the end, we're going to round it to the nearest penny. So multiplying these two together, we end up with $578.29. Let's work that same problem. This time for part B, we want it to be compounded daily. Well, there's 365 days in a year, so N is equal to 365. Let's plug those same numbers then into our formula, just changing the N to 365. So our A is equal to our beginning value, our principal of $500, multiplied by the quantity 1 plus our interest rate, 0.0292, divided by our compounding times per year, which is 365 times, raised to the power of n, 365 times years, which is 5. Again, we're going to multiply this part out all in one step in our calculator. And let's see how that looks. Do that with our calculator. We are going to take our quantity 1 plus 0.0292 divided by 365 raised to the power of 365 times 5. And we get 1.157189, and we could have a couple of extra places there. And then we're going to take that answer and go up and capture that answer, multiply it by 500, and I get $578.59. So with a fairly low interest rate and only 5 years, our difference in our final value is only about 30 cents. Let's do a couple of other examples, 2 more examples. How much money would you need as an initial value if the money was invested at 4% annual interest and compounded monthly for 5 years to end up with $10,000? So this time we want to know how much money we start with as an initial value. We don't know what P is. We're looking for our principal. And the other values that we know, we have an interest rate of 4%, and 4% is the decimal 0.04. We want to compound monthly, that's 12 times a year, so n is 12. And our time is 5 years. And we want to accumulate, at the end of that period, we want to accumulate $10,000. So let's plug those numbers into our compound interest rate formula, which again is A equals P times the quantity 1 plus R divided by N raised to the power of N times T. This time we know A is 10,000. We're looking for P. Our quantity is 1 plus 0.04 divided by 12. And we're going for 12 times 5, or 60th power. So again, we're going to calculate this part all at once. When we do our quantity raised to the 60th power, we get 1.220997. And then solving for P, we want to divide both sides. So we're going to take this and divide both sides by 1.220997. And we get a principal, or a starting value, of $8,190.03. So starting with an investment of $8,190.03, invested at 4% annual interest rate, compounded monthly for 5 years, we would end up with $10,000. In an initial growth model, the ratio between terms of consecutive values of x is going to give us the constant growth rate. For the following table of values, we want to find the constant growth value, or the growth factor. And once we find that, we want to write the exponential growth equation. So let's see what the ratio between consecutive terms is for each one of these. Between x's 1 and 2, we would have the ratio of 9.41 divided by 3.36, which comes out 2.80. 0.006. Between the values of x equals 2 and x equals 3, we have the ratio 26.34 divided by 9.41. And that gives us 2.7991. Between the x values of 3 and 4, we have the ratio 73.76 divided by 26.34. That gives us 2.8003. If we round this to 3 digits, which is our accuracy that we have here, each one of these to 3 digits gives us 2.80. So our growth rate is a constant 2.80. This is our value for B. This is our growth factor. Okay. This represents, by the way, a growth rate of 1 plus that, so 2.80 becomes 1 plus 1.80. That's a growth rate of 180%. For our equation, here's our value for B. So right now we have y equals A times B, 2.80 to the x. What we need to know is our initial value A. This is our value when x is 0, not when x is 1. So I don't have that value for A. So what I can do is I can use the ordered pair 1, 3.36, and I can solve for A. So let's use the ordered pair 1, 3.36. Let's put 1 in for x and 3.36 in for y and solve this equation for A. So we have 3.36 equals A times 2.80 raised to the first power. Well, anything raised to the first power is itself, so this is just 2.80A. Dividing both sides by 2.80 gives us an A equal to 1.2. Our equation then is y equals our value for A that we found here, 1.2, multiplied by our base that we found was 2.80, raised to the power of x. And those are exponential growth models.